Hello, Matt 4110 and 5110 enthusiasts, also the TAs and Dr. Kim Rogers. Matthew Kennedy here doing my Module 8 discussion board, which is about non-Euclidean geometry. And we're going to be going into depth about two prompts that we have the choice to choose from. And we'll just be talking about it really in a sense of what kind of interested me. The one thing I'll say very informally first is just kind of how just unique non-Euclidean geometry is and what what challenge it brings from the fifth postulate of Euclidean geometry. And it kind of just goes back to the whole calculus thing of module 7 and how there's a whole history behind it in the development of calculus. Well, there's also a history behind non-Euclidean geometry and how it was derived after Euclidean geometry and how they saw that fifth postulate, which, by the way, just for reference, the fifth postulate really says there exists a point that is not on a given line and it's going to be parallel such that the two lines never intersect. And that was challenged in a sense where we go to spherical geometry, hyperbolic geometry on 3D planes, a z-axis, if you will, and how when you draw lines, because remember, Euclidean geometry had its own definitions. It's its own, like, almost realm, if you will, in a geometric sense in the math world. We then go to non-Euclidean geometry. It's almost like new rules. Like, it's like going from football to rugby. Like, there's a ball, it looks similar, but how you go about it is it's different. Different rules, different ways to play. Just like with, non-Euclidean versus Euclidean geometry, when you do with a flat plane and really straight lines of a triangle, for what the definition of a triangle is, it can't be a curved side in Euclidean geometry. Well, it really could be in a spherical geometric sense. So, without getting too off track here, I want to respond to I want to really make it clear what specific prompts I'm responding to. So the first prompt is, if there was one or two ideas or points of emphasis that were confusing or unclear to you, please explain. And then also, what was new or most interesting to you, and how did it change the way you think about or perceive things? So the one thing that really was, we'll go into what really interested me the most. It's just the fact that you really think about on non-Euclidean geometry, just how the definitions change from Euclidean geometry to non-Euclidean geometry. So you think about, like, for example, here on page 192 of Hodgkin's book, we refer to this as the Esker model. So it's not really the best photo because I know you guys probably can't see that well, but you kind of just we see this like circle. And let's talk about what Hodgkin refers to. Note, the reader who has no idea of what non-Euclidean geometry is, let alone what a model of it might be, should consider the well-known picture Circle Limit 3 by Esker, which again, Esker was the artist of, he wasn't really the person who came up with, these ideas. He was pretty much like the artist. And I picked up on that from the first video from Wales University, from Professor Wildberger. So we go to we go back to the Hodgkin quote here. In this, which is a picture of non-Euclidean geometry's version of a plane. So this is like the plane of essentially non-Euclidean geometry. So it talks about, the one thing that really interested me was how all the triangles and all the fish are to be considered as having the same size. So again, I know it's kind of hard to really show the diagram, but you see numerous fish on this diagram. And just from looks, the fish, they look like different sizes. But it's an optical illusion, almost. They're all the same size. It's just some look smaller because of how distance works in a non-Euclidean sense. And the one thing that I'll say is like proving, you know, why the distances are different, all that stuff. Like, that's tough. Like, I know it was talked about with Wildberger and how he proved, this was like by the 40-minute mark in his video. It talked about how if I have a spherical geometry, right, a spherical plane, right, if I have a line and I have 2 points, 0, 1, that distance, if I translate that to figure out where 2 is, where 3 is, where 4 is, you see that as we go on from n to n plus 1 distances, it gets smaller and smaller and smaller all the way up to infinity. And you go, now this is looking from a 2D sense, right? A sphere is 3D, but when you look at it from a 2D standpoint, as you go farther and farther and farther and farther across that line, the distance unit becomes smaller and smaller from 3 to 4, 4 to 5, 5 to 6, all the way to n plus 1. You really think about how that distance, like, it's amazing at how I can draw a small fish towards the end of that line, because there is no end to it, right? It goes to infinity. But how that area equals a big fish in the middle of the sphere. It's all perspective, right? So that really interests me, and it just stood out to me. Because, and in talking about how, because the prompt also says, how did it change the way you think about or perceive things? Well, this even goes into triangles. And it, you know, you know, I'm going to say a couple things that interested me because it wasn't just the distance stuff. In K through 12 grades, we were taught a triangle is always going to be 180 degrees, all 3 angles. But the one thing we have to realize is that is in Euclidean geometry. Okay, sorry, I have an itch. But the one thing I'll say, though, is it really amazes me when you think about how, let me see right here. This was in Hodgkin's book in page 200. The angle sum A plus B plus C is always greater than pi. And then also it is talked about in the 3rd video, alpha plus beta plus gamma is greater than pi again. So that's 2 different sources to find that finding in a spherical triangle. It's pretty much 3 points on the spherical, like on the sphere. You connect those 3 points, and how the angles are always going to be greater than pi. And it really interests me just because of how, now see, this is kind of a 2-in-1 prompt because we're supposed to answer 2 prompts, right? And the other prompt says if there was 1 or 2 ideas or points of emphasis that were confusing or unclear to you, like, that's also, it's confusing to me. Because it's like, first of all, what, like, I just don't understand that. Like, it's interesting, but it's also confusing. Like, I don't really understand how, like, and then also I believe it was in a hyperbolic triangle, how it's less than 180. So it's like, I mean, I could be wrong there, but like, that's why it's confusing to me. Like, I don't really understand, you see what I'm saying? Like it's just confusing to me. You know, I don't really understand how, first of all, you can prove that. And if they did prove it, I missed it. But is just very interesting to me. It's also interesting to me about how we define definitions in non-Euclidean geometry. Look at the famous Poincaré disk model, which is in hyperbolic geometry. A line is represented and defined as an arc of a circle who ends up perpendicular to the disk's boundary. And I got that from, again, Wildberger's video from Wales in the first video, and it really interested me about how essentially that is pretty much what a line is. And you think about Euclidean geometry and the definition of a line, it's a lot different, isn't it? So, also parallel lines. Parallel lines really don't exist in spherical geometry, and yet you better believe they exist. And one line with a given slope will have exactly one, well, I guess there could be infinite copies and they're all parallel, but there exists at least, like, there exist parallel lines, right? But in spherical world, in non-Euclidean geometry, it's interesting to me about how there could be no parallel lines. So, putting it really all together without going on too many tangents here, because I don't want the video too long, like, it's in answering those two prompts, what's interesting, what's confusing, everything. Like, I mean, not everything, but like, pretty much, like, I'm so used to Euclidean geometry, I'm so used to, you know, 180 degrees triangles. I'm so used to, you know, well, also in the third video, which I'm not really sure who did that, but the third video, I'm not sure what university that was, but I know it was a doctor professor, but he talked about how if in the spherical world, when you have similar triangles, they have to be congruent. Think about that. In Euclidean world, we think about similar triangles versus congruent triangles. Congruent triangles, all the angles are the same, all three sides are the same. We go to non-Euclidean geometry, it's almost like similar but opposite. Similar triangles are congruent triangles. So really, if you have two triangles that have the same angles, they have to be the same size as well in terms of their outside side lengths. And the reason why is, you know, it goes back to Esker's photo of the fish. The fish, the triangles, they look different, but because of the way a sphere is from perspective and the way triangles are constructed in spheres, if you have the same angles, it's going to be constructed as such where the sides have to be the same, because that's just what the rules are in geometry in non-Euclidean world. So on a parting note here, under 15 minutes, the one thing I'll say with on a parting note is what really interested me, probably even like I know I said the distances kind of interested me the most. Really what interested me the most is actually how we present non-Euclidean geometry to math students from a future teacher mind. I don't understand why Euclidean geometry is just the end-all be-all for grades K through 12, and then in college, it's really when we really start talking about non-Euclidean geometry, a little bit of Calc 2, hyperbolas, Calc 3, little bit in modern geometry, but not as much, definitely in history of math right now. I wonder why they choose that. So that could also be a point, it's a little bit more hypothetical, but in responding to one thing that's kind of confusing or unclear to me, Dr. Tim Rogers, TAs, but no one wants to respond to this. Why do you think that? why do you think that we really go about and really choose, okay, Euclidean geometry is, and non-Euclidean geometry is kind of overlooked? I'm not saying it doesn't exist. I'm not saying non-Euclidean geometry does not matter. It's just, yeah, I get it. In my notes, I wrote it down. Yeah, I understand now. Spherical triangles are different than the traditional Euclidean triangles of 180 degrees and also the areas and all that stuff, and similarity, congruence. But I don't understand kind of like the whole application as to why we utilize Euclidean geometry over non-Euclidean geometry. Like, why do we really emphasize Euclidean geometry? Why is that like recognized more than non-Euclidean geometry? Is it because we just choose that? Like, we're gonna go with Euclidean, like kind of like a base 10 system. Is it kind of just what we went with, or is it like, is there really a real reason? Give me your thoughts. Take care. Bye bye.